Hello class, this is section 6.3, the Taylor and Maclaurin series. And in this section, what we're going to learn is that a function, if it has derivatives of all orders, then we can represent a function with a Taylor series, which is just a power series. Okay? So let's just suppose that some function f has a power series. Okay? And a power series, if it exists for a function, is unique. That was one of the theorems in section 6.2. But let's suppose that I have a function f, and it has a power series, and this is a power series expanded about some a. All right. Now, if we evaluate the power series at a, then all of these terms here that have powers of x minus a will vanish, and all I'm left with is this constant c0. So evidently, f at a is the constant c0. Remember, this is a power series expansion with these c sub n's. So all you have to do to find c sub 0 is plug in the value a into our power series. So notice that c0 is f at a. Now, how would I go about finding c1, c2, etc.? Well, if I differentiate the power series, right, so I'll take one derivative, and we learned that in section 6.2 you could differentiate these term by term and integrate these term by term because they are just polynomials. Okay, so if I differentiate, the c0 term will vanish, and I'll have c1, right, and then 2 times c2. They're just applying the power rule term by term. So here's my expansion for the derivative of f. Now, if I plug in a, all of these terms here will vanish, and I'll be left with only c1. So evidently, c1 is equal to f prime at a. So f prime at a is c1. So if we continued in this fashion, we took two derivatives of the function f, we would find that c2 would be the second derivative of f evaluated at a. All right, let's do this one more time here, well, maybe a couple more times. Let's differentiate it twice. So here I'm indicating differentiating it twice. And so I just differentiate the step before, so the c1 would vanish. This would be 2c2. This would be a 6c3. Okay, and then, of course, x minus a. So here's two derivatives, and now if I evaluated the second derivative at a, all of these terms here would vanish. Okay, and c2 would turn out to be, let's do the work here. Oops, a little bit too far there. So here, if I put in a here, twice c2 would be f prime double prime at a. So dividing by 2, I get c2. So here c2 would be the second derivative of f evaluated at a divided by 2. So here they do that work here. c2 is the second derivative evaluated at a divided by 2. Okay. Let's see how they got c3. So if I differentiate the power series 3 times, okay, look up ahead here, this would just become 0. This would become 6c3. Okay. Here this would become, the 2 would come out in front here, this would be 24c4. Right? 12 times 2 is 24c4, and there's the x minus a, etc. Okay. So now again, if I put a into the third derivative of f, these terms here would all vanish, and I would be left with 6 times c3 is equal to f triple prime at a. Dividing by 6, I would get c3. Okay, so that's how they got c3, f triple prime divided by a. And in general, if I took n derivatives, so here's the notation, f superscript n, that's the nth derivative, and I plugged in a and divided by n factorial, right, you can see that here, the third derivative divided by 3 factorial is divided by 6. The second derivative divided by 2 factorial is divided by 2. Okay? And so to get the cnth term, or coefficient I should say, you simply evaluate the nth derivative at a and divide by n factorial. So in fact, we can find all of the coefficients in the power series and replace it with just f at a, f prime at a, f double prime at a, 2 factorial in the denominator, f triple prime at a over 3 factorial in front of the x minus a cubed, etc. So this is a beautiful way to, in fact, find all of the c sub n's of the power series. Okay. Now, this is called the Taylor series. This is an expansion about a. If you have the special case where you expand about x equals 0, notice A would be 0 in all of these cases, then that's called the Maclaurin series. Okay, so here's the definition of the Taylor series. If f has all the derivatives, so that means it can be derivative at any order, the 80th derivative, the 100th derivative, etc. Then the Taylor series expansion is simply the nth derivative evaluated at a divided by n factorial times x minus a to the n power. That's each term that's added in the infinite series, and you get this sum. If you expand about x equals 0, that's a special version of the Taylor series. That's called the Maclaurin series. Okay. All right, let's do some examples finding Taylor series and Maclaurin series next.